Hi guys, this is Sir Eldon Calamba. So this is another discussion before our sample problem. So let's start. Hi, so this is motion in 2 to 3 dimensions. Okay? This is just a continuation of our motion in 1 dimension, but this time we will be extending it to 2 to 3 dimensions. Okay? For all we know, we have studied about position, velocity, and acceleration. Nothing will change, but one thing that will change is that we have to be mindful that we have now x components, y components, and we also have z components. And then we have to note them wherein it will not be confusing for us. So this time, let's look at this one. We have here in the middle the one dimension, and then on the end we have the 2 to 3 dimensions on how we denote our position, velocity, and acceleration. This time, in our study of motion in 2 to 3D, we will take note of position as R, velocity as V, and acceleration as A. Now, we know that they can be vectors. This position, this velocity, and acceleration, they are just vectors. Sometimes we have to put arrows on top. This one, I'm just talking about the magnitude first, so I'm just putting R, V, and A on what variables that we will be using. Now, but in drawing the velocity, the acceleration vectors, and position vectors, it will be kinda different this time. Okay, so let's have this one. So we have here a curvilinear na path. So we have this path, this red thing, that red path there. So that's the path. Let's say, for example, a particle is coming from point 1 and then going to point 2. We have to note a reference point for us. Let's take note that our reference point, this is just for an example, our reference point is at this point. Okay, hence I wrote my x and y axis. Okay, so from there, I should be making my measurements, wherein how will I put my position R1 and position R2. Always remember that position, it is always coming from the reference point, and our reference point is this one. So we have to put our tail here and then put the arrowhead wherein the particle is initially situated. Same thing with our R2, position R2. Okay, now take notice that our positions, it doesn't just have the x component or the y component anymore. So as you can see, the x and y components is pulled together at an instance at this point 1. You have position along the x, and then you also have position along the y axis, as well as with your R2. Hence, we have to take note of these positions. And for us to take note of these positions, it is better for us to use vectors. So, just a review, we have here vector A, we have the x and y and z components, but we could denote that one using unit vectors. So, we could have here ax I hat, ay j hat, and az k hat. Just take note that I don't have the arrows anymore with above ax, ay, and az using unit vectors because I have the unit vectors already. Okay? So, I could denote this R1 and R2 in terms of these components also. Hence, I have R1 xi hat plus R1 yj hat plus R1 zk hat. As well as with R2. I also have the I hat, j hat, and k hat. So, it will be very easy for us now to make some solutions or to solve some problems. Because we will not have any difficulties now in dealing with these quantities. We could now compartmentalize our solution and our brain that x will not mix with the y as well as with the z, or they should not be mixed together at all because they are in different components, they are in different components. So might as well please remember that just like what we did with vector addition, we cannot mix x with y and y with z and any combination. Okay, now since our particle moves from point 1 to point 2, so there must be a change in position. There must be delta r. And our delta r is pointing from the initial going to the final position. Okay? So, delta r is just like what we did from last time. That is just r2 minus r1, or position in final minus position initial. So, we now have this solution. See, nothing new happened. What just happened is that the solution or the equation for us is getting longer now, because we have understood that there's motion taking place along the x, y, and z at the same time. Okay, so since time is also essential for us, so motion takes a moment to be done. So there's a element of time for that one. So we could get the average velocity. So we have there delta r over delta t. So we have this understanding now that we have average velocity along the x, along the y, and along the z. And ngayon nagsabay silang lahat. So take note, these are vectors. We also have the instantaneous velocity, that is just the derivative of position with respect to time, or that is your dr dt. So you have your initial velocities, not initial, sorry, instantaneous velocity along the x, along the y, and then along the z axis. Okay, so that's how we understand now our motion in 2 to 3 dimension in terms of velocities. Now, in terms of acceleration, we will have to make use of this illustration pa din, but I will just have to write first the velocity vectors. Now, if you have a curvilinear na path or curved path, your velocity vector, these are v1 and v2 here, is that these are instantaneous values. This will always follow this will always follow, or the tail will always be connected to the particle itself. And then, our velocity vectors, they are always tangential to our path. Okay, so that's why, as you can see, my v1 and v2, they are always tangential to our path. So, same thing, as you can see, your v1 and v2 is not just on the x-axis and y-axis. So, you could also have it in terms of unit vectors. You have there v1 and v2 in terms of I hat, j hat, and k hat. This is what I call the in terms of unit vectors na notation. Okay? And then you also have your delta v, that is just v2 minus v1, because we have to take the average acceleration, and that is delta v over delta t, as you can see with this one, delta v over delta t. And you have also your, I made a boo-boo. This should be acceleration. This should be A. Okay, so you have your average acceleration sa X, average acceleration sa Y, average acceleration sa Z axis. And this one also, this should be, that's correct. For the instantaneous velocity, so you have your instantaneous, that is dv over dt, and it should follow. You have your velocity vectors here, your velocity quantities. And take note, these are in terms of in terms of unit vectors. Using the idea of vectors now, we could actually get the magnitude. And the magnitude is just using the Pythagorean relationship. For example, you want to get the magnitude of our instantaneous acceleration. So that is just the absolute value of A instantaneous equal to the square root of ax squared plus ay squared plus az squared. Now you have your magnitude. But in terms of direction, it's kind of difficult for us to note the direction if it is 3 dimension. But if it is in 2 dimension, you can make use of your SOHCAHTOA. Okay, for me, I suggest the tangent pa din. Now I forgot to take note of the acceleration, the average velocity vector. Always remember your average velocity vector, this one, VAV, the direction of your VAV is dependent on the direction of delta R. Because between the displacement and time, it is the displacement that is vector. So the direction of your VF will follow the direction of delta R. Hence, your delta R is pointing from R1 to R2, or so from point 1 to point 2. So your average velocity is also pointing towards the same direction as delta R. Okay, so that's for your average and instantaneous acceleration. Now, for your average velocity, what we're going to do for this one is that we have to connect our V1 and V2 tail to tail. So let's say, for example, this is V1, and then this is your V2. So our velocity vector for your average acceleration vector is coming from this point going to that point. So that is your your average acceleration. We now know how to write your velocity vector and acceleration vector. How average acceleration vector, but how about your instantaneous acceleration vector? Our instantaneous acceleration vector, it's kind of different with the average. Average is pointing towards the same direction with delta V. But for our instantaneous acceleration, still same thing with our velocity vector. It is connected to the particle, okay, wherein the particle is moving, and then we have here the velocity vector that is tangential to the path. But for the acceleration vector, it's kind of different. How different it is that our acceleration vector is always pointing towards the curvilinear path, or towards the curvature of the path. So that's why, as you can see with my acceleration vector, it is pointing towards where the bulge is going, to the concavity of our path, and that is this pink one is our path. Now, as you can see with your acceleration vector, it is pointing towards the curvature, or towards the center of our curvilinear path. Now, please take note that our acceleration vector, instantaneous acceleration, is that we also have components. You have your x and y components, okay? And this acceleration vector is also, we could formalize this component. We could have the parallel component, and then we have the perpendicular component and then we call them as the tangential and then the parallel na component na acceleration. Okay? For all we know, we have to make an axis with respect to our velocity vector v, because these two accelerations will be dependent on v, wherein it is perpendicular to v or tangential to v or parallel to v. Okay, so these accelerations also is the one that is responsible for changing the speed and then changing the direction of our particle. And this one, let's say for example, your particle is moving or making a turn, but then while making a turn, you notice that it is moving at a constant velocity, so or constant speed, so it's not changing, it's not accelerating. But we have to take note also that acceleration is also dependent on direction. Just because your speed is not changing, you are not accelerating. You take note of your direction. Is direction changing? If it is changing, then you are accelerating even though the speed is constant. Okay? So the components of your acceleration vector are actually the ones that is responsible for us to tell na is it accelerating. Okay, so we have the blow up version. Yan. Sorry. This should be the parallel one, and this is the perpendicular one. Sorry. Okay, so we have to make an axis with respect to our velocity vector v, and then you make your x and y, or your axis rather. That's not necessarily the x and y, and then you have to decompose into components your acceleration vector. Okay? So, with respect to that one, as you can see, you have projection you have a projection vector that is perpendicular to our velocity vector v. This is the velocity vector v, and this is the perpendicular component of our acceleration vector. And then we have a component or parallel acceleration that is the component of vector a that is parallel with respect to velocity vector v. These are just projections of this acceleration vector. So you have component here and then component here. Now, this perpendicular acceleration is the one that is responsible for changing direction. Okay? It is as if na parang may humihila sa ating particle para mag-change ng kanyang direction. So, it's the one that is responsible for changing the direction of our particle. And for this parallel acceleration, I will not call it tangential anymore, but parallel. This parallel acceleration is the one you can see as you have observed. It is in the same axis with your velocity vector. It is the one that is responsible for changing the speed. Ayan. So those are your components of your acceleration. You have a perpendicular and a parallel component with respect to our velocity vector v.